I've been asked why we at Linn have decided to design our own drive units. I think it's useful to understand, well, two things. One, a little bit of history, but also our engineering ethos. So, strictly speaking, our engineering ethos is to lose less at the source, and then after there, add nothing. So add no form of distortion, no form of colour, no character, just replay what you've captured at the source. So let's go back a few years and look at a little bit of history of our loudspeakers. In 2013 we introduced Exakt after a long period of development. Now Exakt is kind of an umbrella term for a number of technologies, but the key and most important thing in there is the linear phase performance from a loudspeaker. Linear phase assures perfect time alignment of your loudspeaker. Anything that's incorrect in time equates to incorrect in space. So when you get the time signature of your loudspeaker correct, everything falls into physical place as well. Now, linear phase was the last and biggest form of distortion that we'd not addressed with our active loudspeaker technology before that. Active dealt with a number of forms of distortion in loudspeakers, but it left this one thing that you couldn't fix with any form of analog crossover. So Exakt bought linear phase. And I kind of figured I'd long desired to produce a linear phase loudspeaker, and I thought, well, this will be the be all and end all, everything's going to be perfect, everything will sound wonderful. It did, in many ways it did, but it didn't get me that holy grail of a loudspeaker that just disappeared in the room. And a good few years later, after we'd proliferated Exakt through the range and developed a few other products, we started development of the 360. The 360 is our flagship loudspeaker, and we have driven down distortion everywhere possible. We have adaptive bias control amplification, we have power DAC technology. In the drive units, we've used advanced materials, pushing any audible breakup out of band. We have a phenomenal shape of cabinet, bringing dispersion performance that we've never experienced before, removing the room from the equation. Another form of distortion gone. So having addressed all of those forms of distortion in our flagship 360, we had to look, where do we go next? And for us, it had to be inside the drive unit. It's the inner workings of the drive unit. We knew that the existing motor and suspension systems introduced forms of distortion that we could address. We could do a better job, and that's why we chose to go back to first principles on the design of our new drive unit. There's an interesting thing with an active loudspeaker or an integrated loudspeaker. We fully understand the environment that a drive unit is operating in, and that's quite a rare thing in the industry. So most loudspeaker drive unit manufacturers or suppliers are designing a unit where they don't really know how the thing's going to be used. It could be used in a sealed cabinet, a ported, a transmission line, you don't know. You don't know what size of amplifier is going to be driving the thing, so there's a bunch of variables that you have to kind of look after in your design. You have to be a bit careful with the design to ensure the thing doesn't get damaged. So typically what you see with a normal drive unit or a drive unit bought from a supplier will be that for its total mechanical movement range, and when I say total range, I mean literally as you start hitting metal at the back of the motor and it starts clanking about half of that will be what's described as its linear operating range. The rest of it is putting the brakes on to make sure it doesn't get damaged. Now we're in that position where we know more about how the loudspeaker is going to be used, the drive unit is going to be used, so we wanted to push that linear range far further out. There's no reason to start applying the brakes. We know how hard the amplifier is going to drive it. We know how stiff the spring of the air in the cabinet is behind the drive unit. We know all these things. So we absolutely should be able to do better. We should be able to use more linearity from a drive unit. Now, linearity is quite an important thing to me as an audio engineer, but perhaps most people don't necessarily understand what I mean when I talk about linearity. So, what is linearity and why does it matter? Perhaps more importantly, why does it matter? Linearity is, it's easier to talk about a power amplifier as an example. What you want from a power amplifier is a perfectly flat response, and as you amplify the signal more, you take the signal level up, you get exactly the same response. You're not changing the frequency response, you don't get any added distortion. It's perfectly scalable. So what that would mean for a loudspeaker, if that were also true, is that it doesn't matter what level of playback you drive the thing at, the perceived listening level, as it goes up, you don't change anything in the response. Unfortunately, with conventional drive units and the current, or prior state of the art, should I say, that really wasn't the case. And that's because of this protective layer that gets built into the unit. As you start pushing it harder, the response changes, you add distortion, and you effectively get less level out of the drive unit. It isn't a linear scaling. So that's really what we wanted to go after. So let's consider the 360. We've already got a very good tweeter and mid-range in there. They're both already very linear in their performance within the 360. Neither drive unit has to move very much. They stay well within their linear range. They perform very nicely. So the chief culprits that we really see that are behaving in a non-linear way are the bass unit and the upper bass unit in the 360. So they're the ones that we wanted to focus our attentions on. So now we've established the concept of what we want to do. We know we need to produce the most linear drive units in the world. We need to redefine the state of the art. But to do that, we needed to invest in engineering skills and engineering tools. All groundbreaking development starts with research. So we needed to research how we were going to develop a motor system and a suspension system that gave us the linearity we desire. Existing motor systems had a linear response, what the industry defines as linear response, that we didn't feel was anywhere near linear enough. It had to be a flat line. So the motor force would be a flat line, no matter where the drive unit is in its excursion range. The suspension similarly needed to be a flat line across the whole range of motion that we desired from the drive unit. That's what led us on the path to the pistonic motor system and the very advanced suspension system we have in our new drive units today. So from the research, we go into simulation. We start building simulated models, simulated physical structures of what this motor may be. Many months of simulation effort went into looking at the motor structure initially to get a really broad, flat, truly linear response. And only once we refined the simulation to that degree were we at a position where we said, right, well, let's now prototype this. And a key thing with any simulation is verifying your model. And that's really what the first prototype does. You build a prototype that's based on this simulation, you measure the response of it, and you go, well, something is wrong here, something doesn't tie together. And you go back and you correct your simulation. You've made assumptions about the permeability of the steel, the strength of the magnet, the different things in this structure. Some of those will be slightly wrong. So you end up in this iterative cycle where all the time you're refining your simulation. It's getting more and more close to reality, more and more a digital twin, as we call it, simulating that real world thing. So after a few iterations, we were at a point where we're confident enough with our simulation of the motor that we were like, right, this is right now. If we build this, it will do what we want it to do. We will have a truly wide and linear response, arguably the most linear response available to us in the world. So during that iterative process, we also started looking at the suspension system. Our target was to produce a mirror response, if you like. So for the extremes of the motor force linearity, we want a flat performing suspension, the same stiffness for the same amount of excursion, and only then do we stiffen up and stop the unit from any kind of potential damage. So about 18 months in, we had the motor structure that we wanted, and we went on to prototype the suspension system. We didn't even know at that stage if you could produce such a linear suspension. No one else seems to, so we weren't sure if it was possible. When we actually prototyped that first suspension system, again, our models were somewhat off, and as my simulation engineer put it, we seem to have designed a Ferrari with no brakes. So we needed to go back round that loop again. Feed those results into the simulation, develop the simulation, and arrive at something that is going to give us a linear spider that doesn't end up in a bush. So that iterative process of simulation and prototyping has led us now to a motor system which we believe is the most linear, truly linear motor system in the world. That's pistonic. And we have this super advanced suspension system for our drive unit, which is also probably the most linear in the world. We now need to put those together to actually produce a drive unit. Again, here we get into iteration. The first time we did it, it didn't really work quite the way that we'd expected. The drive unit produced an awful lot of noise that we weren't expecting. The voice coil wasn't travelling straight and true through the motor. It was rattling off the sides. It wasn't what it needed to be. We could see we had the excursion that we wanted. We could see the linearity there, but there was a lot of noise from the drive unit. Now, this is where we started needing to almost reinvent the manufacturing process for a drive unit. Typically, a drive unit is assembled in a very simple way, with one centering jig down the middle of the voice coil onto the motor, and everything just gets glued on that as you go up through the drive unit. That wasn't good enough for us. We had such a long travel of the coil through a narrow gap in the motor. Everything had to be perfectly consistent, perfectly concentric, perfectly perpendicular. So at every stage of building up this drive unit, we developed new jigs, machined from steel and aluminium to keep things absolutely flat, absolutely true, perfectly concentric, and only then did we actually arrive at a drive unit that met all of our goals. So the realization that we'd achieved our goal came with a degree of frustration. One of the early production batches that we'd attempted, we built 30 units. One of them worked as we'd intended. The other 29 all had issues. So it allowed us to measure one unit, and the measurements were astonishing. They were exactly what we'd hoped for. Harmonic distortion, intermod distortion, so much lower than we'd seen in other units. But frustratingly, we couldn't listen at that stage. But it gave us motivation to fix that production process. So then we would have enough units to actually populate a loudspeaker and see what the audible result was going to be. So what is the audible result? It's pretty astonishing. It's a process for me. I have to take the new units, dial them in, put them into the loudspeaker, get them all working together as a system. So that sudden realization doesn't really happen for me until I do an A/B demonstration against the existing 360 loudspeaker. And that was the point where I realized, we've done something genuinely special here. The level of clarity through not just the bass, but through the entire vocal range. I'm flabbergasted by the results, and I designed them. You've got to go and have a listen to these loudspeakers.